GCSE AQA Chemistry, Topic 6. Rate of reactions, with 3 required practicals, position of equilibrium, and Le Chatelier's principle.
Topic 6. The rate and extent of chemical change. The rate of chemical reactions is determined by the speed the reactants are changed into products. E.g., iron rusting is slow, but burning is fast, and magnesium plus acid is in the middle. You can find the rate of reaction by recording the amount of product formed or reactant used up divided by the time. The steeper the line, the faster the reaction. When the reaction is finished, the line becomes straight. The diagram shown shows the same reaction under different conditions and different speeds. The line that goes flat first is the fastest reaction. Where the line goes together shows the same amount of product was produced, just over a longer period of time. Where the line goes flat higher on the graph shows more reactants were used to make more products. Before a reaction starts to happen, the activation energy must be reached for the particles to collide with enough energy to react. The rate of reaction then depends on 4 things. Temperature means the particles move faster so they collide more frequently. Concentration and pressure both make it more likely that particles will collide as they increase. The higher the surface area to volume ratio, the more frequent collisions. Catalysts decrease the activation energy by providing an alternate place to react, which needs less energy. Enzymes are biological catalysts. One required practical is to calculate the rate of reaction of an experiment. The rate of reaction, remember, is the amount of product divided by the time it took to produce it. The units for this depend on whether it's a solid or gas or moles. This can be centimeters cubed per second, grams per second, or moles per second. There are 3 different ways to measure the rate of reaction. A visual change or colour change in solutions can be timed, but this cannot be put on a graph. E.g., how long a black cross can be seen through the solution. However, this is subjective. A change in mass by gas being given off can be measured by recording the time and mass on scales of the reaction. This can then be plotted onto a graph to find the final rate. The final one is measuring the volume of gas given off by using a gas syringe, in the units in centimeters cubed per second, where you can measure the volume in the syringe and the time. But if the reaction is too vigorous, the pressure can explode or shatter the syringe, so be careful. E.g., magnesium and hydrochloric acid react to produce hydrogen gas. This can be done in 5 steps. Step 1. Add a set volume of dilute hydrochloric acid to a conical flask. Step 2. Add magnesium ribbon to the acid and attach an empty gas syringe to the flask. Step 3. Start the stopwatch. Record the volume of gas in the syringe at 30-second intervals. Step 4. Plot the results on a table. And Step 5. Plot a graph with x-axis as the time and the y-axis as the volume of gas produced. You can then repeat this for different concentrations of hydrochloric acid, but keep all other variables the same. This leaves you with a graph like this, where you can compare the rates of reaction for different concentrations of acid. Sodium thiosulfate and hydrochloric acid produce cloudy precipitate from their originally clear solutions. This is because sodium is produced. Add a set volume of sodium thiosulfate to a conical flask. Place the flask on a piece of paper with a black cross drawn on it. Add dilute hydrochloric acid to the flask and start the stopwatch. Now watch the black cross disappear through the cloudy sulfur and time how long it takes to go. This can be repeated with one of the solutions being at a higher concentration and all other variables being kept the same. The higher the concentration, the faster the reaction, so the less time it takes for the mark to disappear. This reaction, however, will not give you a set of graphs, because you cannot measure how much product was produced. The mean reaction rate can be calculated from a graph by the change in y, divided by the change in x. This means taking 2 points from the graph, finding the difference between them, and putting them into the equation. If you need the rate of reaction at a particular point, however, you need to draw a tangent from the point you want to find the rate of reaction for. Pick 2 easily readable points and find the gradient between them. This is the rate of reaction, e.g. 0.27 grams per minute. A reversible reaction is the one that can go back and forth between the reactants and the products, e.g. A plus B can make C plus D. As the reactants react, their concentration falls, so the forward reaction will slow down. But as more products are made, their concentration rises. The backwards reaction will speed up. When the forward rate is the same as the backward rate, the system is at equilibrium. At equilibrium, both reactions are still happening, but there's no overall change in reactants or products concentrations. This is only reached if it is in a closed system. Nothing can get in or out. Equilibrium does not mean that the amount of reactants and product are equal. When the equilibrium lies to the left, the concentration of products is less than the concentration of reactants. And when it lies to the right, the concentration of products is more than the concentration of reactants. The position of equilibrium depends on the following conditions: the reaction itself, the temperature, the pressure, if involving gases, the concentration of reactants and products, e.g. ammonium chloride into ammonia plus hydrogen chloride. Heating this produces more products, and cooling it produces less. In reversible reactions, if the reaction one way is endothermic, the reaction the other way is exothermic. The energy given out / taken in on either side of the equation is equal. E.g. hydrated copper sulfate can make anhydrous copper sulfate plus water. It is endothermic in the forwards reaction and exothermic in the backwards reaction. Le Chatellier's principle is that if you try to change the conditions in a reversible reaction at equilibrium, the system will try to counteract the change. It can be used to predict any changes you make to a reaction system. Number 1, the temperature. If you decrease it, the reaction will move in the exothermic direction to produce more heat, e.g. in making ammonia, where the forward direction is exothermic. A decrease in temperature increases the amount of ammonia made. Number 2, pressure, only with gases. If it increases, the equilibrium will reduce it by moving to the side with the fewest molecules of gas, e.g. in making ammonia, N2 plus 3H2 can make 2NH3. There are less molecules on the product side, so if you increase the pressure, more ammonia is made. Number 3, concentration. If the concentration of reactants is increased, more product is made, and vice versa. E.g., in making ammonia, the reactant's concentration increases, the more ammonia is made. This is a very complicated principle, so it is important to practice lots of exam questions on this, and I will have some linked below.
Don't forget the MINDMAP is ready to download in the description. Don't forget to subscribe for more GCSE AQA chemistry content and more revision tips. Thank you for watching. I will see you in the next one.